direct variation in word problems might say directly proportional to, varies directly as. It's all about setting up the variation equation. So this is another way of thinking about proportionality. Let's take a look at this very first problem. If x varies directly as y, and x equals 18 when y equals 6, find x when y equals 7. So right off the bat, if x varies directly as y, we need to know how to translate this. X varies directly as y is almost self-explanatory. X is x, y is y, but we can't just put equals. When we see a variation statement, we need to have something about our constant of proportionality k. So it's not just equals, it's equals k. X varies directly as equals k, and for direct, we multiply y. So why do we always have to set it up with this statement? Why do we need to have this k in here? Well, we're going to use the next bit of information, x equals 18 when y equals 6, to solve for k. So if x is 18 and y is 6, divide both sides by 6 to solve for k. Here, k equals 3. So now instead of x equals ky, we have x equals 3y. And we use this now to finish the problem off. Find x when y equals 7. So plug 7 in for y. And we get that x is 21. Let's look at another one. Number 2, I have z varies directly as x squared. So let's translate that. Z varies directly as x squared. So direct variation equals k, and then we keep in the same line, keep multiplying. They tell us if z equals 36 when x equals 3. Okay, so we stop there to solve for k. Plug in 36. Plug in 3 for x. So 36 is 9k. Divide both sides by 9. We get k equals 4. So z equals 4x squared. We take that value for k, plug it right back in to get our direct variation equation. So there is proportionality at work, but we solve it using the variation equation. The final part of this number 2 says, find z when x equals 5. Find z when x equals 5. So 5 squared is 25, order of operations. We get z equals 100. Now, if direct variation is multiplying after the k, inverse variation is going to be dividing by the k. And number 3 here, z varies inversely as w, and z equals 20 when w equals 0.8 Find z when w equals 10. We're going to break it down the same way. First, a translation. Z varies inversely. So instead of multiplying after k, we're going to divide after k. Inversely as w. And z equals 20 when w equals 0.8. And then we're going to find z when w equals 10. So plug in what we know. Z is 20. W is 0.8. To solve for k, we would multiply both sides by 0.8. 20 times 0.8 is 16. So k is 16. Plug that back in. Z equals 16 over w. So what's z when w is 10? It would be 16 over 10. 16 divided by 10 is 1.6. Number 4. Z varies inversely as w squared. Z equals 10 when w equals 4. Find z when w equals 3. So first, z varies inversely as w squared. Z varies inversely, divide, as w squared. Don't forget the square. We're told z equals 10 when w equals 4. Plug in 10 equals k over 4 squared, 16. To solve for k, multiply both sides by 16. That's k equals 160. Plug that back in. Z equals 160 over w squared. And then the rest of the problem said, find z when w equals 3. 3 squared is 9. We have 160 over 9. We're told to simplify our answer. That doesn't divide evenly. We can just make 160 over 9 the answer. So in 5, y varies jointly as s and v squared. Y varies jointly as s and v squared. So joint variation is just more than 1. We can also have combined variation. And combined would be if we have direct and inverse, if we have multiplying stuff and dividing stuff. So the numbers they give us, when s equals 7 and v equals 5, y equals 700, we're going to want to find y when s is 11 and v is 9. So for joint variation problems, they have to give us more information. Because if we're looking for one thing, they need to give us everything else. First, we use all 3 points they give us, data values, to plug in and solve for k. So y is 700, k is unknown, s is 7, v is 5, so v squared is 25. 7 times 25 is 175. So 700 equals 175k. 700 divided by 175 is 4. So 4 is k. Plug that back in. Y equals 4s v squared. So what is y when s is 11 and v is 9? V squared would be 81. 4 times 11 times 81. Whew. y is 3,564. The weight m of an object on the moon varies directly as its weight e on Earth. A person who weighs 153.24 pounds on Earth weighs 26.05 pounds on the moon. How much would a 231.76 pound person weigh on the moon? So if we read that first sentence, the weight m varies directly as the weight e. M varies directly as e. M varies directly as e. A person who weighs 153.24 pounds on Earth, so when e equals 153.24, they weigh on the moon 26.05 pounds. So m is 26.05. Then we want to know what's m, what's the moon weight of a person with an Earth weight of 231.76. So what's m when e is 231.76? So we pulled this out of the word problem. And we do it just like we did before. Plug in what we have so we can solve for k. 26.05 equals k times 153.24. Divide both sides by 153.24. So 26.05 divided by 153.24 is 0.16999. I think we can call that 0.17 without worrying about a rounding error, no problem. So, m equals k, 0.17, times e. What is m when e is 231.76? 0.17 times 231.76 is, and it tells us here to round to the nearest tenth, 39.399. That's 39.4. The volume of a can is directly proportional to the height of the can. If the volume of the can is 400 cubic centimeters when the height is 14.62 centimeters, find the volume to the nearest whole number of a can with height 16.92 centimeters. So pull out what we need. First, the first sentence tells us the volume of a can is directly proportional to the height of a can. Let's call volume V and height H. V is directly proportional to H. V is directly proportional to H. If the volume is 400 when the height is 14.62, find the volume when the height is 16.92. So there's the information. Nothing's changing with how we do it, though. V is 400, K times 14.62. Divide both sides by 14.62. 400 divided by 14.62 is 27.3597. So like 27.36. Plug that in for K. V equals 27.36. H. What is V when H is 16.92? So we have to do 27.36 times 16.92. We want to round this. It says do not round until the final answer, then round to the nearest whole number as needed. 462.93, that's going to be 463 cubic centimeters. Number 9. Over a specified distance, rate varies inversely with time. Let's get that part down. Rate varies inversely with time. If a car on a test track goes a certain distance in 1/5 minute at 175 miles per hour, so time is 1/5 of a minute, the rate is 175 miles per hour. What rate is needed to go the same distance in 2/3 minute? What will be the rate if the time is 2/3? So plug in what we know. R equals K over 1/5. Oh boy. To undo dividing by 1/5, we would multiply both sides by 1/5. So 1/5 R equals K. And actually, even though I can solve it that way, we saw that working with literal equations, I forgot to plug in R. R is 175. So 175 equals K over 1/5. Dividing by 1/5, undoing that is multiplying both sides by 1/5. So we would have ended up in the same spot anyway. 1/5 times 175 is the same as 175 divided by 5. Which is 35. So K is 35. R equals 35 over T. What is R when T is 2/3? Again, since we're dividing by 2/3 and we want to undo that, multiplying both sides by 2/3 will do that. 2/3 R equals 35. Unnecessary, unless you need to see that we're multiplying by 3/2. Fractions, am I right? So this is 105 over 2. Which is 52.5. Since we were dealing with fractions the whole time, instead of 0.5, we really should say 52.5. The current in a simple electrical circuit is inversely proportional to the resistance. So the current is inversely proportional to the resistance. C is inversely proportional to R. C is inversely proportional to R. If the current is 40 amps, when the resistance is 3, so C equals 40 when R is 3. Find the current, C equals what, when the resistance is 7.2 ohms, when R is 7.2. Okay, same problem as always. R is 3. C is 40. Multiply both sides by 3 to get K. K is 120. So C equals 120 over R. What is C when R is 7.2? 120 divided by 7.2 is 16.66666666, which we know is 2/3. So 16 2/3 amps. The amount of time it takes a swimmer to swim a race varies inversely with her average speed. A swimmer finishes a race in 375 seconds with an average speed of 4 feet per second. Find the average speed of the swimmer if it takes 500 seconds to finish the race. Okay, so the amount of time varies inversely with speed. Time varies inversely with speed. A swimmer finishes in 375 seconds. So when t is 375, the speed is 4 feet per second. We want to find the speed when the time is 500. So another word problem, but we pull out the same information. So 375 equals k over 4. Multiply both sides by 4. We get that k is 1500. Oh. Just plugging in k. T equals 1500 over s. What is s when t is 500? Oh, s. Do you also have difficulties writing 8s when you're trying to write s's in math because math is numbers? Jeez. Okay, so we have t equals 1500 over s. We want to know when t is 500, what is s? Now, this is a little bit different than what we've done before, because now we're solving for something that's still out here. So first of all, the s is on the bottom. Let's multiply both sides by s. 500s equals 1500, and now we can divide both sides by 500. S equals 3. 3 feet per second. Now, again, that was different because normally those ones we were doing, the thing we would plug in would be on the right side, and we'd just do the math. But here, it was t that we had, and we were looking for s. Let's do one more. The distance that an object falls when dropped varies directly with the square of the amount of time since dropped. Distance varies directly with the square of time. D equals kt squared. An object falls 88.2 meters, so D is 88.2, in 3 seconds when t is 3. Find the distance. What is d? It falls in 5 seconds when t equals 5. So 88.2 equals k times t squared. T is 3, so times 9. 88.2 divided by 9 is 9.8. That's a physics number. Putting it back in, d equals 9.8 t squared. We want to find the distance when t is 5. If t is 5, that means t squared is 25, and 9.8 times 25 is 245. 6,245 meters.
The body mass index, BMI, of an individual varies directly as the weight of the individual and inversely as the square of the height of the individual. The body mass index for a 156-pound person who is 65 inches tall is 25.96. Determine the BMI for an individual who is 72 inches tall and 175 pounds. Round to 2 decimal places. So what's important is that very first sentence. We need to write it out using K as a constant of variation, multiplying by things that are directly proportional, direct variation, dividing by things that are inversely proportional, inverse variation. So the body mass index, BMI, of an individual varies directly, so multiply by the K, directly as the weight of the individual and inversely as the square of the height of the individual. So the body mass index is varying directly as the weight and inversely as the square of the height. Then we're told the body mass index for a 156-pound person, so when W is 156, who is 65 inches tall, so 65 squared, square of the height, is 25.96. If we square 65, we get 4,225. So 156K over 4225 is 25.96. If I multiply both sides by 4225, 25.96. I get 109,681 is equal to 156K. And then if I divide both sides by 156, I get for K 703.08. So BMI is 703.08 W over H squared. All of that to solve for K, to plug it into the equation. This is now the equation we're going to use to determine the BMI for an individual who is 72 inches tall, that's the height, and 175 pounds, that's the weight. Remember, we're going to round our answer to 2 decimal places. That's why I did 2 decimal places here. So W is 175. Height is 72. The BMI is 703.08 times 175 over 72 squared. $123,039 over 5,184. Gives me a BMI of 23.73. The objectives of this topic are evaluate exponential functions, graph exponential functions, evaluate functions with base E, and use compound interest formulas. The exponential function f with base b is defined by f of x equals b to the x, or y equals b to the x, where b is a positive constant other than 1, and x is any real number. The exponential function f of x equals 42.2 times 1.56 to the x models the average amount spent. It's an exponential function because the exponent is the variable. So when the variable is in the exponent, that's an exponential function. This function f models the average amount spent in dollars at a shopping mall after X hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? Well, X is the number of hours, so we substitute 3 for X and evaluate the function. You will need a calculator for these problems. So how this would work is that we are going to take 1.56 and we are going to raise that to the third power. Keep that answer in the calculator and then multiply it by 42.2. We get approximately 160.208755. And we want it to the nearest dollar. So this rounds to 160. So about $160. Again, when we evaluate these, we don't do 42.2 times 1.56. That would be multiplication first. Order of operations says we do the exponent first. So raise the 1.56 to the third power and then multiply the result by 42.2. Then do whatever rounding the problem requires. Let's look at the graph of an exponential function. And anytime we want to do a graph of something new, we can do a table of coordinates and then plot the points. So let's use some x values, -2, -1, 0, and 1. And let's find out what the function values are at these x values. So plugging in -2, that would be 3 to the -2, or 1 over 3 squared, 1 over 9. Plugging in -1, that would be 3 to the -1, or 1 over 3 to the first, 1/3. Anything to the 0 power is 1. And anything to the first power is itself. So 3 to the 0 is 1. 3 to the 1 is 3. That gives us some points to graph. -2 1/9, -1 1/3, 0 1, and 1 3. Plot those points, and we can kind of see this shape that's forming. The exponential function has a horizontal asymptote. And when it's in standard form, when it's just base to the x, that horizontal asymptote is the x-axis. And again, if we just have base to the x, anything to the 0 power is 1, so the point 0, 1 will always be there. So a horizontal asymptote at the x-axis, the point 0, 1, and then this shape. From left to right, we rise very slowly, and then we rise very quickly. Exponential growth is very fast growth. So the domain of f of x equals b to the x, some base to the x power, consists of all real numbers. We saw that on the graph. At -infinity, we had graph, and at +infinity, we have graph. It's just going to be way up there. The range was just all positive real numbers. Where did the graph exist? It only existed above the x-axis. It's never going to touch the x-axis. The function value is never going to reach 0. But all values above 0 up through +infinity are accounted for y values. So the domain is all real numbers, and the range is 0 to infinity, not including 0. And as I mentioned, the graphs of all exponential functions of the form base to the x pass through the point 0, 1, because anything to the 0 power will give us 1. The y-intercept is 1. There is no x-intercept, because again, it never touches the x-axis. If our b is greater than 1, we have a graph that goes up to the right and increases forever and ever. The greater the value of the base, the steeper the increase. If our base is between 0 and 1, b to the x has a graph that goes down to the right and is a decreasing function. So if our base is between 0 and 1, we have a horizontal flip of the usual graph. It still goes through 0, 1. It still has an asymptote at the x-axis. It's just we're starting up at +infinity and we're coming down through 0, 1, approaching the asymptote as we go from left to right. We say that f of x equals b to the x is a 1-to-1 function and has an inverse that is a function. And we can see it passes the horizontal line test. The blue graph does, and so does the fuchsia, magenta, purple graph. Remember, functions that pass the horizontal line test have inverses. And we keep talking about this horizontal asymptote. But let's make that official. That horizontal asymptote does exist. Just like all of our other shapes, we can transform them. We can do a vertical translation By adding or subtracting from b to the x, up or down. By adding or subtracting just from the x in the exponent, we can move it left or right. By taking the opposite of the entire function, we could reflect about the x-axis, do a vertical flip. By taking just the opposite of the x, we can reflect about the y-axis. We can do a horizontal flip. So nothing new there, just a new shape. And we can stretch and shrink vertically and horizontally our new shape as well. Same rules as before. If the c we're multiplying the entire function by is greater than 1, it's a vertical stretch. If it's between 0 and 1, it's a vertical shrink. If the c we're just multiplying our x by is greater than 1, it's a horizontal shrink. If the c we're just multiplying the x by is between 0 and 1, it is a horizontal stretch. So let's use the graph of f of x equals 3 to the x to obtain the graph of f of x equals 3 to the x minus 1, where the x minus 1 is all the exponent. Well, if we're just subtracting from the x, that's a left or a right movement. Subtraction is not going in the negative direction. It's actually going in the positive direction. Minus 1 is right 1. So start with what we know about our graph of 3 to the x. It has a horizontal asymptote. At the x-axis, it goes through the point 0, 1. If we want to move this 1 to the right, all of these points move 1 to the right. We can imagine 0, 1 is now at 1, 1. And we still draw through that point. Keep our horizontal asymptote. Rise forever to the right. Again, a shift of 1 to the right adds 1 to our x coordinates. So the more points we had on the original graph, the more points we can shift and draw our new graph. Let's talk about E. E is something we refer to as the natural base. And it's defined as the value that 1 plus 1 over n to the n approaches as n gets larger and larger. This has some financial implications and some financial formulas. As n approaches infinity, the approximate value of e to 9 decimal places is approximately 2.718281827. So 2.71828 or 2.72 if we want to round it to just 2 decimal places. So we call that the natural base, and e to the x, therefore, is called the natural exponential function. The exponential function f of x equals 1.1, f of x equals 1,144 e to the 0.0325x. Models the gray wolf population of the Western Great Lakes X years after 1978. Project the gray wolf's population in the recovery area in 2014. So the population is f of x. The number of years after 1978 is X. We want to project the population in 2014. So first we need to figure out that 2014 is 36 years after 1978. That's just some subtraction. And because it's 36 years after 1978, that means 36 is our X. We plug that in. Again, when we're plugging in, we want to take care of the exponent first. And in the exponent, we have 0.0325 times 36. That gives us 1.17. So then we need e to the 1.17. And then we need that times 1144. And that gives us 3,685.959578. That's going to round to 3,686. This indicates that the gray wolf population in the Western Great Lakes in the year 2014 is projected to be about 3,686 wolves. So again, multiply the exponent first, then do base to the exponent, and you'll want a calculator that has e to the x as an option. And then you'll multiply that by 1,144. If you don't have e on your calculator, that's okay. 2.72. It'll get you close. The more digits of e that you use, the closer you'll get. After T years, the balance A in an account with principal P and annual interest rate R in decimal form is given by the following formulas. For n compounding periods per year, in other words, if it compounds quarterly, n would be 4. If it compounds monthly, n would be 12. We use the formula A equals P times 1 plus R over n to the nt. And remember, E, if we go back, was defined as the value that 1 plus 1 over n to the n approaches as n approaches infinity, as n gets larger and larger. So we can start with n equals 1, compounding annually. And we can move that up to n equals 12, compounding monthly. N equals 52, compounding weekly. N equals 360 or 365, compounding daily. If we make that go all the way up to n equals infinity, well, that can't happen. We can only approach infinity. That becomes e. And we can see 1 plus 1 over n to the n looks like it's a major part of this formula 1 plus r over n to the nt. And in fact, once all the maths, continuous compounding, where n actually is infinite, gives us the formula A equals P times e to the RT, the PERT formula, continuous compound interest. A sum of $10,000 is invested at an annual interest rate of 1.08%. Find the balance in the account after 5 years, subject to quarterly compounding. Okay, we're compounding quarterly. That's 4 compound periods per year. N is 4. We're going to use what I call the apparent formula because it kind of looks like the word apparent. A equals P times 1 plus R over N to the NT. P is the principal, 10,000. R is the rate as a decimal, 0.0108. N is 4. T is 5 for 5 years. So how do we put this in the calculator? Take care of the exponent first. 4 times 5 is 20. Inside the parentheses, we have 0.0108 divided by 4. So we'll do that, and then we'll add 1, and then we'll raise that to the 20th. Finally, we'll multiply that by 10,000, and we'll get 10,554.07798. This is money, it rounds to the nearest cent. 10,554 and 8 cents. I can verify I just did this on the calculator. That is what we get. So the balance in the account after 5 years, subject to quarterly compounding, will be $10,554.08. Now, it's only natural that we're going to take this same principle, this same interest rate. We're going to see what happens if we have continuous compounding. So let's bring out the PERT formula. A equals P times E to the RT. Plug in what we have. P is 10,000. R is again 0.0108. T is again 5. This time we're going to do 0.0108 times 5. We get 0.054. We're going to raise E to the 0.054. We're going to multiply that by 10,000. And we get 10,554.84602. This is money. It rounds to the nearest cent, $10,554.85. So the balance in the account after 5 years subject to continuous compounding is $10,554.85. Compare that to just compounding quarterly. That was 10,554 and 8 cents. Not terribly more. The interest rate is pretty low at 1.08%. We did get more cents out of it, though. But the point is, the continuous compounding is the better option. If you could ever get continuous interest, definitely go for that. Remember, compound interest takes the interest you've earned and adds it to the account that earns interest. So interest earning interest more when it's continuous. Okay, that's it for this topic. The objectives in this topic are change from logarithmic to exponential form, change from exponential to logarithmic form, evaluate logarithms, use basic logarithmic properties, graph logarithmic functions, find the domain of a logarithmic function, use common logarithms, use natural logarithms. So when we talked about exponential functions, functions where the variable was in the exponent, we mentioned that they were 1-to-1 and therefore had an inverse. The logarithmic function is the inverse of the exponential function. So for x greater than 0 and b greater than 0, b not equal to 1, y equals log base b of x is equivalent to b to the y equals x. And I'm going to make this make so much sense. Don't worry. But right now we say that the function f of x equals log base b to the x is the logarithmic function with base b. So in logarithmic form, we have y equals log base b of x. A logarithm is an exponent. Anything you need to know to make logarithms make sense is comprised in that statement. A logarithm is an exponent. Now, what do I mean by that? What do I mean by a logarithm is an exponent? Well, if we look at exponential form first, b to the y equals x. Our base, our exponent. Whatever the exponent is in exponential form is what the log is equal to. A logarithm is an exponent. The base is the base. The x is the thing that's left over. So let's just jump into some examples. 3 equals log base 7 of x. Well, the base is 7. What's our exponent? It's what the log is equal to. The log is equal to 3. The exponent is 3. So base 7, exponent 3 equals the thing that's left, equals x. That's all there is to the translation. In B, 2 equals log base b of 25. The base is b. The exponent is what the log is equal to. Log is exponent. Log is 2. Exponent is 2. Base b, exponent 2 equals the thing that's left, equals 25. In C, base 4. Logarithm is y. Logarithm is exponent. Exponent is y. Base 4, exponent y equals the thing that's left, equals 26. Now we can go both ways. This was logarithmic to exponential. We can go exponential to logarithmic. The base here is 2. The exponent is 5. A logarithm is an exponent. Here the logarithm is 5. 5 equals log base 2 of what's left, of x. 5 equals log base 2 of x. In B, the base is b. The exponent is 3. That's equal to 27. A logarithm is an exponent. So 3 equals the log. The base is b. 27 is what's left. And then for C, the base is e. The exponent is y. The logarithm is the exponent. Y is the logarithm. Y equals the log base e of what's left, 33. Now, knowing what the alternate form is going to look like gives us a little bit of a shortcut when it comes to evaluating logs. In A, we have log base 10 of 100. Log base 10 of 100 being some number means that log base 10 of 100 is some exponent. A logarithm is an exponent. So to evaluate a logarithm, we're looking for an exponent, specifically the exponent of the base, which happens to be this smaller number 10. So 10 to what power is 100? That's going to be 2. 10 squared is 100. So log base 10 of 100 is 2. So we're looking for the exponent that turns the little tiny number into the great big number. Here in B, we want to turn 5 into 1 over 125. Turning a number into a fraction means we have a negative exponent. 5 to the third would be 125, so this must be -3. 5 to the negative third is 1 over 125. So log base 5 of 1/125 is -3. $36 to what power is 6? That's what we have to ask ourselves when we look at log base 36 of 6. Well, how do we go from 36 to 6? Using powers, not multiplication or division. We could take the square root. The square root of 36 is 6. What power is the square root? 1/2. So since 36 to the 1/2 power is 6, log base 36 of 6 is 1/2. So now that you understand logs, they're kind of fun. Fun meaning quote unquote easy. The hard part is understanding. Once you understand the log, you can tackle the log. Log base 3 of the 7th root of 3. Ooh. Well, we know that that means that 3 to what power is the 7th root of 3? It might be helpful to think of the 7th root of 3 as the 1/7 power. So 3 to what power is 3 to the 1/7 power? Well, that's just going to be 1/7. 3 to the 1/7 power is 3 to the 1/7 power. We have some basic logarithmic properties involving 1. Log base b of b is 1 because b to the first is b. And log base b of 1 is 0 because b to the 0 is 1. Anything to the 0 power is 1. Anything to the first is itself. So we can use these properties to simplify some logs. Log base 9 of 9 is 1 because 9 to the first is 9. Did we really need a special property for that? If we know that the base raised to some power is 9, if we know that 9 raised to some power is 9, that power must be 1. We can just logic that through every time. We don't have to memorize log base b of b equals 1. We can, but as long as we understand how the log works, we already know that it's going to be 1. And log base 8 of 1, 8 to what power is 1? Anything to the 0 power is 1. So 8 to the 0 power is 1. Log base 8 of 1 is 0. Again, we didn't need to memorize log base b of 1 is 0. We just needed to know that 8 to the 0 power is 1. We just needed to know that that's what the log form means. Similarly, we have some inverse properties of logarithms. We can consider this as the exponent and the log canceling each other out. Log base b of b to the x just leaves us with x. We saw this with that 1/7 problem. B to what power is b to the x? Well, b to the x is b to the x. So it's like the log base b and the base b cancel each other out, just leaving us with the exponent x as a full-fledged number, not an exponent. Now, base b to the log base b of x, canceling out the log base b and the base b, that's the best way to think about that one, I think. So we can undo logs by raising them as exponents of their base. How would we use these properties? Well, in A, log base 7 of 7 to the 8th, the log base 7 and the base 7 cancel each other out, just leaving us with 8. Or you can think 7 to what power is 7 to the 8th? 8. In B, we have a base 3 raised to a log base 3. The base 3 and the log base 3 cancel each other out, just leaving us with 17 out of the exponent and into the actual numbers. Now, earlier I mentioned that the log is the inverse function for the exponential. So log base 3 and base 3, when we graph them in the same coordinate system, should be reflections of each other over the line y equals x. Because recall, that's what inverse functions look like when we graph them. Symmetric about that diagonal y equals x line. So first, we'll set up a table for f of x equals 3 to the x. This is very familiar to us. -2, -1, 0, and 1 could be our x values, giving us 1/9, 1/3, 1, and 3 as our y values. We can just reverse these coordinates for the inverse function. We don't have to figure out logs of specific numbers. We don't have to plug things into the log function. Because if xy is in one function, then its inverse would have yx. The x and the y switch. That's why it's reflective over y equals x. So for the log, we can use x's of 1/9, 1/3, 1, and 3, and get function values back of -2, -1, 0, and 1. Graph them both, and we see that they are symmetric about that line, that diagonal y equals x. So here's what the log looks like. It has a vertical asymptote of the y-axis, and instead of going through 1, 0, it goes through 0, 1. Sorry, instead of going through 0, 1, that's the blue point. It goes through 1, 0. That's the red point. X comes first. Come on. Ugh. So yeah, vertical asymptote of the y-axis, 0, 1. 1, 0. Ugh. That's so hard to keep straight. Do you struggle with graphs like I do? Let's talk about this graph. So the domain is all positive real numbers. The range is all real numbers. That's the exact switch of the exponential function's domain and range. Look at the red graph. The domain, we have no x's to the left of 0. We never hit 0. So only things greater than 0 for x are defined on the red graph. Meanwhile, though, it goes all the way down to negative infinity, and slowly but surely it will make its way up to positive infinity. So the outputs would be all real numbers. They all pass through the point 1, 0, because f of 1 would be log base b of 1, and anything to the 0 power is 1, so that would be equal to 0. The x-intercept is therefore 1, and there is no y-intercept. As we'll state later, that's going to be because of that vertical asymptote. If b is greater than 1, the graph goes up to the right and is an increasing function. But if b is between 0 and 1, if it's like 1/2, log base 1/2 of x, that would be a graph that goes down to the right and would be a decreasing function. And the y-axis is a vertical asymptote. Now, going back in time, looking at this graph of the log again. Since there are no negative x's, since there is no 0 for x, they're not in the domain. We can't plug them into the log. The log function will not take any negative numbers, and the log function will not take a 0. So if you're asking for the log of 0, if you're asking for the log of a negative number, those don't exist because 0 and the negative numbers are not in the domain. So in example 7 here, we're going to find the domain of a logarithmic function. Specifically, we're going to find the domain of f of x equals log base 4 of x minus 5. The base 4, that's not important. We don't need to know that information to find the domain. We know that the log can't take 0 and the log can't take negative. Kind of similar to square roots. Square roots can't take negatives, but they can take zeros. And just like finding the domain of a square root, when we find the domain of a log, we find what we can have by first finding what we can't have. We can't have negatives. We can't have zeros. We can only have positive values. So x minus 5 must be positive. X minus 5 must be greater than 0. So we have x minus 5 is greater than 0. Add 5 to both sides. X is greater than 5. So the domain of this function would be 5 to infinity. And we can kind of sketch a graph to show this. Subtracting 5 inside from the left is a movement of 5 to the right. So we take our normal logarithmic shape and we move it 5 to the right. The vertical asymptote moves to be at 5. And it goes through 6, 0 instead of 1, 0.